Any? The recording? Okay. So, okay. Welcome you all for the School of Physical Sciences seminar series. Today we have the speaker, Professor Heejun Yang, who is the professor at Korea Advanced Institute of Science and Technology, South Korea. He was awarded IUPAP Young Scientist Prize in Semiconductor Physics in 2018 for his outstanding contribution to the novel interface devices based on the structural electronic quantum state control with van der Waals layered materials. He is a member of Korea Academy of Science and Technology. He received his PhD in physics on the spectroscopy of graphene by scanning tunneling microscopy and spectroscopy from Seoul National University and University of Paris in France in 2010, and he had some experience for the industries as well. So he worked in the Samsung Electronics from 2010 to 2012. He worked on the graphene spintronics with Albert Fert, who was a Nobel laureate in 2007, and in his group at CNRS Thales as a postdoc. And with his research background on molecular and nanometer scale studies in Seoul and Paris, and the electric and spintronic devices of the physics of those devices in Samsung and CNRS Thales, he moved to Sungkwon University in 2014, and he worked there until 2021. And then he joined KAIST in 2021, where he started working on the original device studies with phase engineering of the low dimensional materials. And he has proposed a novel and conceptual interface device such as graphene barristers, which is published in Science, and ohmic homojunction contact between semiconductor channel and metal electrodes, which is published in Science in 2015. So we welcome you, Professor Heejun Yang, for your address, and we are looking forward for your talk. So after your talk, we'll have some question and answer session. So the online participants can type their questions in chat box. So, maybe you can start now. Thank you very much.
Thank you very much, Professor Ajay Soni, and for this invitation. And especially Juhi Pandey, Dr. Juhi Pandey is working in our group, and I sometimes discuss about her activity in IIT Mandi, so it's my great pleasure. So I'm Heejun Yang, as Professor Ajay Soni kindly introduced. So today I will talk about some of my recent 2D device studies. Here I put two pictures. I hope maybe someday I will invite you to KAIST. This is a summer and fall picture of our campus. So generally my research direction is to develop tolerant, energy efficient, semiconducting very small devices or quantum devices. I'm not studying this quantum computation or quantum physics, but here we hear a lot. Nowadays, many people are studying this quantum computation, and then they are studying some physical system models, and then they are looking for some more tolerant qubit system. And also in semiconductor industry, like Samsung, TSMC, Intel, they are making smaller and smaller devices, you know. And then now they are approaching 3 nanometer regime. And then fabrication itself, already it's difficult to have reliable production level, industrial level things. And also device operation, we have many quantum phenomena. As we decrease the size of the device, many atomic defects or some unique things happens which has not been observed in classical system. So I want to address these kind of issues, for example, with 2D materials. So let me show you this picture. For example, if we have silicon 3D materials, we see clear FCC diamond structure in silicon here. But we have dangling bonds. If we decrease the thickness again and again, we will have different materials properties, different band gaps or things like that. But if we use atomically thin materials, we can assemble, we call it van der Waals heterostructures, which is a good way. And also in my presentation, I will emphasize the use of momentum. Momentum of electrons. Momentum is also a good quantum number. But if you think about battery, for example, we are applying some chemical potential of electrons. Generally, in your computer or cell phone, you are using diffusive current. We have more electrons and then less electrons, and then we have this electron flow. But maybe in this small scale, ballistic transport or momentum, using momentum would be a new direction to develop devices. So let me introduce myself as well as my research for tolerant quantum energy devices. As Professor Sonny introduced, I did STM in my PhD. That means I'm studying condensed matter physics, but from bottom up. I'm studying atoms and then very small scale, and I'm building up. And in Samsung, I reported graphene barrister. This is one example. If you look at this TEM image, we clearly see silicon atoms, but we don't see graphene because this is one only atomic sheet. But you don't see silicon oxidation here. Native silicon oxide is not visible because graphene as a 2D material passivates well the silicon, which is very reactive to oxygen. If we make this special Schottky junction, this is a Schottky junction between a semiconductor silicon and a semi-metallic graphene. We have a Schottky barrier height like this. But you know, in graphene, we have quite small number of density of state. So if we accumulate electrons or holes in the graphene, we can shift up or shift down the Fermi level of the graphene, which means we can make a smaller Schottky barrier height and a larger Schottky barrier height, which can be used as on and off. Graphene doesn't have a band gap, but it's a sort of barrier variable transistor, so we name it barrister. But I will not go deeply about this topic today. And also, after my PhD in Samsung, Albert Fert, he is a great scientist, and then he suggested me to do some spintronics magnetism study with 2D materials. So I spent some time with him at Dallas. And then I was interested in some phase transition. So layered material and then some no dangling bonds or very tunable Schottky barrier height. Also, we have phase transition between metal semiconductors. This is another unique property of 2D materials. So last year, it was my great honor I made a presentation in the Centennial Symposium last summer in this IUPEP Symposium. And then in 20th century, we developed the quantum mechanics, and then we now have electronic engineering based on silicon. But now we are having more and more new materials, and then physicists to make contribution again, can make certain contribution again. This is what I hope to do in future. So based on this motivation and 2D materials, my device physics study include some barrister. And this is another example here in this channel. You know, silicons are semiconductor, and we are using copper for electrode in our device. But silicon and copper, they are different materials, but sometimes in 2D materials, we can have semiconducting channel and metallic electrode in a single material. This is what I reported. And then I'm also studying some synaptic devices, emulating our brain. And also I'm doing this STM study. Basically, I'm trying to utilize various benefits of 2D materials to address this quantum mechanical device study. But in my presentation today, I will present three recent works about orbital gating, as the title says, and also some resonant tunneling spectroscopy and the device operation. Okay, So let's start my first topic, resonant tunneling at the device scale. As I said, we have current flow, mostly diffusive current flow in your device. We are using chemical potential of electrons. And what about tunneling? Some scientists, engineers are developing tunneling transistors, and they sometimes use this word, resonant tunneling. So resonant tunneling means if we have source and drain, and if we have some energy matching between two levels available state, we have more efficient tunneling. This is called resonant tunneling. This can be homo-lumen levels or some specific state, and then you can make this energy matching. This is what we did with many 2D electron gas in gallium arsenide and aluminum gallium arsenide interface something. What about momentum-dependent transport, as I mentioned in my first slide? In my understanding, in my opinion, one pioneering example is this one. So when we study graphene by STM, we have to make tunneling current vertically from the tip to the graphene. So the tunneling electrons are moving vertically. But once the electrons enter the graphene, they should flow in plane. Momentum should be in plane. So this gamma point to K point, we need a sort of momentum change, and this is called inelastic scattering. And then inelastic scattering takes place, and then we can see it as sort of bandgap-like feature. So in my understanding, this is one of the first examples to show momentum effect in transport. But we can develop this idea further to use this new degree of freedom in our device operation. And another thing is in condensed matter physics in university and grad school, we learn block theory and band structure. They are, we say, delocalized. Delocalized means atomic orbitals, they are combined and then they make some delocalized bands. But you know, we have some localized state or localized bands even. So this is one example of a carbon nanotube. You see, over several nanometer, band gaps. The blue areas are band gap area. Band gaps are changing. So in low dimensional materials like 1D, 2D materials, this is quite susceptible to the external environment. And then the band structure can be different from place to place. So this is MOS2, very famous 2D material, 2D semiconductor. And band gaps are very, very different. This could be some local strain, local defect, and many other regions. Okay. And then you also have heard some, of course, optical microscopy you are using. We have some lateral resolution. And Raman spectroscopy, somehow we have lateral confocal Raman spectroscopy and vertical resolution. Sometimes you can imagine angle reachable photoemission spectroscopy, which can be also done locally. But as I said, if we are playing with 2D materials, sometimes we are making some stacking vertical devices. How can we study the vertical electronic band structure, dispersion, and some vertical resolution? So this is important, especially for vertical heterostructure devices. For example, we can have graphene, boron nitride, gold. This is one example of vertical electrode. If we apply some strong electric field to operate the device, and what could be a good way to study this localized band structure and device operation? This is one my open question as well. So I'm saying many things, but this is another introduction. Think about this bilayer graphene. So we have two atomic sheets. And then this is not from our group. Some people prefer this bilayer MOS2. And then this is their band diagram. We have some tunneling. But interesting thing is here, there are two conduction bands and two valence bands from bilayer MOS2. There are two layers, but it's like we have a voltage drop between the two layers. But one way to think about this situation is bilayer graphene is a single material. Okay, so it should have some combined band structure, not like this voltage drop, like different components in electronics. But in other sense, this is a van der Waals interaction, dipole-dipole interaction, quite weak interaction. So they could be treated as separate two materials with this voltage drop. This is what I wrote here, tricky van der Waals interaction. But actually, physicists know the answer. So in the MOS2, bilayer MOS2, there are many kinds of electrons. For example, K-valley electrons, electrons with K momentum in the reciprocal space, and also electrons with Q-valley, Q momentum, okay, in the reciprocal space. And K-valley electrons, they are mainly from sulfur atoms here. The molybdenum atoms here. Molybdenum atoms are these green color. They are quite far apart. They don't interact each other. So their K point electrons, they are degenerate. Degenerate means upper layer, lower layer, they are degenerate. But if we apply vertical electric field, we have some electron displacement, and then we can break the degeneracy. Now we have sort of a voltage drop between the two layers. It's because this molybdenum atoms electron and this molybdenum atoms electrons, they are not interacting quite seriously. But what about these sulfur atoms? They contribute Q-valley electrons. And then you see they are quite close each other. And chemically, if we approach two atomic orbitals, we have bonding and anti-bonding feature. This is important thing. So we have bonding and anti-bonding like split of the band. It's because they are interacting a lot. So this feature, this kind of voltage drop is valid for K-point electrons like this. So somehow K-point electron, Q-point electrons, they have different orbital geometry, topology. This is related to my talk title, orbital gating something. You will see more. Okay, so the first experimental result from our group is like this. We made MOS2 monolayer, and here we have some 2D insulator, HBM, hexagonal boron nitride. Interesting thing is that these two MOS2 monolayer, they were from one single body. This is called the pair and stacking method. We pair one MOS2 flake and we keep the orientation of the lattice and we make this stacking. So here the one unique thing is two MOS2 layers. The lattice orientations are well aligned. Maybe you have heard about graphene magic angle or something. When we make this vertical heterostructure, we can control relative angles. Okay, so this is a different thing compared with STM. In STM, we are using this tungsten tip and then we study some sample. There is no momentum resolution. We cannot study momentum, you will see. But here we have same lattice structure tunneling. So this is what we do. And then if we measure tunneling current between two MOS2 layer like this, here we have one electrode, here we have the other electrode. The result is like this. At low temperature, at room temperature, we have current increase as we increase the voltage and some shoulder feature here. And then suddenly current decreases, even though we are increasing the voltage. So we call it, this is called negative differential resistance. Okay? It is quite weird. Why current decreases even though we are increasing the voltage? Actually, in physics, this is coming from some resonance phenomena, and we can explain it like this. So initially, we have some proper Fermi level alignment like this, and then if we increase the source drain voltage, that means this is the Fermi level, and the Fermi level difference is what we apply, the source drain voltage. And let's look at this peak current. The maximum current happens when the band diagram aligns like this. We have electrons and we have empty state. So electrons can tunnel into the empty state. Okay, but if we increase more the voltage, now the band diagram is like this. Okay, so here the voltage is high and electrons can find their room, empty state. So we can make some tunneling current. But the problem is here they are from the same material, same orientation. So even though we have this energy matching, their momentums are not matching. Here, this is approximately quadratic band dispersion. So if we have this electron tunneling, the momentum, okay, momentum here in the x-axis, they are not matching each other. So we have less efficient tunneling current. That's why we have this tunneling current decrease. So I call it, this is not only energy matching, but also momentum matching resonant tunneling phenomena. So as I said, initially from the beginning, so now we are using momentum degree of freedom of electrons in this material. Of course, if we you don't, it's hard to see there are some technical things. For example, can we shift the Fermi level freely in the band gap, which is not possible for N-type silicon and P-type silicon. We have some Fermi level pinning. But here we have nice property of 2D materials. We have no dangling bonds. We can freely shift the Fermi levels. So this is one evidence. If we look at all voltage range, we have some current saturation because we have reverse direction. But I will not go deeply here. So we have this momentum-driven transport, and then we can make this Fermi level shift inside the 2D material band gap. So actually, it's similar to the quantum mechanical Stark effect. So if we use bilayer MOS2 here, and then we are applying certain electric field, and if you imagine this bilayer MOS2, now instead of a single layer in the previous case, now we are using bilayer MOS2. So the vertical electric field would accumulate electrons in one layer because we are applying electric field. And then we will have this degeneracy breaking, okay? So even K-valley electrons under an electric field, we have some charge displacement, and then we can break the degeneracy. And this was discovered in hydrogen atom, and then this is called the Stark effect, So in 2D materials, we have a similar phenomena, and then we have this degeneracy breaking. And this is what we say DFT, first principle calculation. We have bonding and anti-bonding feature at Q point. And then here, Q point, K point, if we apply some electric field, the bilayer MOS2, they split their band. So what happens in the bilayer resonant tunneling device? Here we have two peaks. Actually, these two peaks are coming from K2 between Q valley and K valley. Of course, their momentums are not exactly the same, so they cannot make a peak. They can make only shoulder feature. And then here we have a more blunt peak. It's because here we have K point energy matching, but momentums cannot be perfectly matching. So we have more blunt feature here. So we can have these two shoulders from these two split bands between Q valley and K valley. So if we estimate physically the energy difference between the two bands by the giant Stark effect, so it's less than 70 milli eV, 70 milli eV. And this is room temperature data. Room temperature means we have thermal energy fluctuation of 25 milli electron volt. So this tiny energy difference between two bands could be measured with a large source drain, this voltage bias, and then shoulder feature. So this is one advantage of this momentum-driven resonant tunneling. This is called the giant Stark effect because in hydrogen atom, the energy split is order of milli-eV. Here we have tens of milli-eV, so more than 10 times larger. Okay, this is one part of my talk. I have speed up. I have two more topics, but they are easier. So let's think about graphene quantum Hall effect, Landau levels. I hope you are familiar with this topic. And Landau levels happens if we apply high magnetic fields. But if we apply 1 Tesla, for example, this is also a high magnetic field. The energy difference, energy gap between two Landau levels would be sort of 30 millieV something. But we can never observe Landau levels at room temperature at 1 Tesla things. So to see Landau levels or quantum Hall effect at room temperature, we need 30 Tesla, which is quite challenging in our laboratory, in your laboratory. So what's the reason? We know also the reason because of the charge puzzles. So if we make this nice graphene device, this is another important property of 2D materials. We have a highly doped region and less doped region, and they are making charge puzzles. So all Landau levels are being broadened by the charge puzzles. So we need a very high magnetic field. So what can you do that? So I developed this one single defect resonant transistor, which is interesting. This is based on resonant tunneling as well. So now I have single layer graphene layer and single graphene layer here. They are also prepared by pair and stacking method. From one graphene flake, we tear the graphene flake, and then keeping the graphene lattice orientation, we make this stacking. So we can have energy and momentum resonant tunneling here, as we discussed. And then what you should all know is that in all materials, we have defects. Defects are everywhere, and more defects exist in 2D materials. So in this HBN tunneling barrier insulator, we have some defects. This is well known. So what about transport? Here, you see we are using graphene edge contact here to reduce the contact resistance. And then we have tunneling. And you see some hopping-like things. This is tunneling. And we are doing some top gating of the top graphene layer like this. Okay, this is the experimental result. Graphene, 0 degree orientation. So this is mapping. This is a differential conductance mapping. So we see some change very sensitively. The y-axis is top gate bias and x-axis is bias. Bias means between two graphene layers. So let me explain the meaning of this mapping. Here we have bright lines. Actually, these bright lines happens because we have more efficient tunneling somehow. And then we know the origin. Here we have some defect state. And then if tunneling happens via the defect state in the HBN, we have more efficient tunneling. That's what we see, the bright line. And what about this bright line? Let's follow this bright line with positive slope. In this positive slope, we are increasing VB. Increasing VB means in this parallel capacitor, we are accumulating holes. Okay? But if we increase the top gating bias here, we are accumulating electrons. So if we follow the line, somehow we have compensation. We are accumulating holes from the bias, and we are accumulating electrons from the top gating. We have charge compensation. That's why we have this positive slope and negative slope from the bottom graphene. Anyway, this is resonant tunneling, and similar data have been reported as well. But you see the left mapping simulation. This is what we simulated. So this is very simple. We just use MATLAB, Mathematica, very simple coupled equation. So we can simulate just considering the energy difference between the two. And then they look quite similar, surprisingly. And in the paper, I wrote like this about the defect state in the HBN. The single point defect energy is 90 millieV above the direct point of the bottom graphene. And the single defect state is located around the center of the HBN layer, but 3% closer to the top graphene. They are too detailed, right? So this detailed information, how can you get it? It's from the simulation, of course. So some people are studying defect state in some media, and for 2D materials, this is, as far as I know, most detailed information about defect state. I'm proud of this finding and simulation. Okay, but if we use some general graphene layer without our intentional lattice matching, for example, 21 degree, this is intentionally made. We have some very, very different things because we have some random resonant tunneling. Of course, we see X-shape. They are from graphene's Dirac point, which is quite robust. Whatever the momentum is, we can see. But another thing here, imagine quantum dots, 0D physical objects. In quantum dots, there is no momentum concept. We have only energy. Quantum dot is a zero-dimensional structure, so we cannot make any momentum because there is no period. So here, if we have this point-like defect in the HBN, and then we have K-valley electrons in the graphene. So how can we have this momentum tunneling, resonant tunneling here? So my interpretation of my data is like this. We have some series of defects in the HBN. And then somehow, by chance, we have certain period, maybe 10 defects with certain period. And if you do the Fourier transform, this period could be interpreted as momentum. So we can select. Of course, we cannot allocate a certain defect series, but this was made naturally. But we have very few defect series with certain momentum. Anyway, we have this phenomena, and then the result is, of course, if we apply vertical magnetic field, we have Landau rebels, and they are Landau rebels, and this is quantum Hall effect. And then quantum Hall effect, of course, with this Dirac velocity, we measured it. And then here, quantum Hall effect could be measured at 300 Kelvin. I like this room temperature quantum things. And the reason is here, as I said, we have quite few defects. Few defects with certain period for matching the K momentum of the electrons in the graphene. We have a very little chance. So somehow we select a certain area of the graphene channel. This is tunneling between two graphene layers. We have large area, several micro by several micrometer, but we have a certain defect location with a certain period. And then we can select certain area of the graphene channel, which has uniform Landau rebel, no Landau rebel broadening. So we can measure it, the Landau rebel difference at room temperature at 2 Tesla. So I like this result because we could measure it at room temperature. And then physically, if we compare the energy with 2 Tesla, the separation is about 40 millieV, and we have 25 millieV energy fluctuation. So this is the maximum that we can do physically in our device. Okay. So let's go to the last topic of my presentation today. This is orbital gating. So let's first think about optoelectronic device and some light illumination. So we can make device and then we can illuminate light. And photovoltaic happens. For example, we have electron hole pairs. They are sometimes called excitons, and we have dissociated exciton dissociation, and then we have current increase. So in general, if we have semiconductor device, if we shine some light, we have more current. This is called photoconductive effect. Okay. And another effect is called the photo gating effect. If we illuminate some light, we have charge trap. And then these trapped charges are gating the channel again. So the result is we have, this is called the transfer curve. So for semiconductor, NB plus semiconductor, we have this transfer curve. And then if we illuminate light, this transfer curve can be shifted in terms of gate bias. So in this case, sometimes we have lower current on the light illumination. And sometimes we have higher current under the light illumination. And in most cases, they are mixed. So instead of MOS2, somehow we use the MOT2, but the physics is the same. So MOS2 and MOT2, they are 2D semiconductors. And then, as I said, we always have some defect in the HBN layer, and we have some screening. In condensed matter physics, this is called the screening. But when you learn the Thomas Fermi screening in condensed matter course, we assume electrons are not interacting each other, and we have screening length, okay, Debye length. But here, in this case, depending on the orbital nature inside the MOT2, K-valley electrons and Q-valley electrons, they have different interaction between atomic layers. So we cannot freely apply Thomas Fermi screening theory here. So if we have, for example, trapped holes in the HBN, we have accumulated electrons in the first layer, second layer, and if we calculate the electron density function, depending on the layer, the first, second, third, we have some screening. So we have some electrons in the first layer. So the x-axis electric field, this is applied by the trapped charges in the HBN. For example, here, we have some large electron accumulation in the first layer and less electron accumulation, second, third, fourth layer. So what does it mean? Here, we have a built-in potential or built-in electric field, which is very important for photovoltaic solar cells or other things. So if we illuminate light, we have photocurrent based on these K-valley electrons, not Q-valley. This is the key. That's why I named it orbital gating. We can selectively accumulate electrons at the K-valley, not Q-valley, okay? So actually, all the scientists, they are also very intelligent. So I like this survey of all the science. And then, for example, 1947, we know silicon surface state, 7x7 structure, and we have some trapped charges, trapped electrons at the silicon surface. And then they already knew this surface band bending. Here we have some atomic termination of silicon surface atoms. And then thanks to this, or due to this termination of atoms, we have special atomic arrangement and then surface state, and we have some charges. And then this charge make a band bending like this. But here, this depletion width is about 100 nanometers something. But in the previous page, I showed you 4 atomic layers. 4 atomic layers, it's like only 3 nanometer. So it's interesting to control electric field and charge accumulation in this small dimension. Anyway, the schematic is like this. We have some momentum dependent or orbital dependent built-in potential like this, electron accumulation. This is the vertical screening. And if we illuminate light, we have a built-in potential for K-valley electrons. So we have this accumulation here. And then they make some tunneling current through HBN. So we can gate only the top MOT2 layer separately from the bottom 3 layers. So this is called the giant stack effect because we have level splitting by charge displacement. And then we can turn off for the last 3 cases. Okay. So this is the result. We have dark current. First, enjoy this ambipolar behavior. If we apply positive gate bias, we have electron channel. If we have this negative gate bias, we have hole channel. So hole exists in the conducting channel. And then this is called the transfer curve. And then we have a shift under the light illumination. The shift is coming from this doped or gated top MOT2 layer. So the thing is, this is, maybe you can call it photo gating effect, but in photo gating effect, except our work, they all involve some charge traps. Trapped charges and detrapping, we need some time. So on-off cannot be so fast because we should use some charge trapping. But in our device, the on-off is quite fast because we are accumulating charge and then freely move by this built-in potential. And then we have, this is called some efficiency. Responsivity is quite high. So we have this new orbital gating phototransistor device. So some of you maybe know the Kelvin probe force microscopy, and maybe many of you are doing this technique as well. But one unique thing in our group is we illuminate light during this measurement. So we measure the surface potential under the light or in the dark condition, and we compare this quasi-Fermi level or the quasi-surface potential. So we could study, for example, the dark thing. So the y-axis for the dark signal, this can be considered as a work function. So really, the 2D materials, depending on the thickness, we have different work function. And then we measure the surface photovoltaic signal, surface potential difference. So they are constant because they are determined by the defect density of the HBM. So we could explain all our result by this orbital gating. So this is the conclusion, last page. So in this presentation, I wanted to show you our recent device work. So we want to study some new momentum-driven transport phenomena, and then electron wave function. So we call it quantum device, but not many people would agree. But anyway, we want to use some benefits of 2D materials, and we want to develop some tolerant quantum device, for example, room temperature, lambda level device, things like that. Okay, that's all. Thank you for your attention.
Yeah, thank you very much, Professor Yang, for the very excellent talk, and really mean like some of the results were very impressive, considering the fact that the two-dimensional materials, of course, are very interesting because of the density of states, and see, like some of the heterostructures are really good, especially looking at the cross-section TEM. So now I think the session is open for the question and answer.
Yeah, any question, basic things are okay. I welcome.
Yeah. We have a Professor Orko Roy. He's
Professor Yang, thanks for the nice talk. So I was wondering that the slide that you showed on quantum oscillations, is it something similar to the Friedel oscillation?
Quantum oscillation?
Yeah, I mean, I was wondering that if there's an equivalent to the Friedel oscillation that one sees in Fermi systems.
Friedel oscillation. So in my PhD, the topic is Friedel oscillation in graphene. I like this term. And Friedel oscillation is basically screening behavior of electrons. We have electron C, and if we have certain defect, and then we have scattering, and we have constructive interference with certain period. This is, here we assume very weak interaction between electrons. So we have some electric interaction and then screening behavior. But in our device, when you consider this screening, we should use some DFT calculation. Unfortunately, we cannot have these screening lengths like a Friedel oscillation in metals or semiconductors. The reason is here we have van der Waals interaction. So the orbitals, we have some overlap, but they are interacting by some external dipole-dipole interaction, and some electrons are interacting and some electrons are not interacting. So we have to separately treat the or conduction electron, for example. So it's not like a copper or other things which can be described by Friedel oscillation. I'm not so sure this is the proper answer for your question, but this is what I understood.
And also, when you talk of tolerant language, are these tolerant?
Sorry, so the connection was bad, so I couldn't hear you well.
Again, you showed that your devices will be useful for making tolerant.
No, I don't hear your voice. Sorry.
Yeah, hello, can you hear me?
Yeah.
Yeah, at the end you showed something that your devices would be useful for making.
Oh, stop it again.
Yeah, so his question is on the last slide which you showed.
Yes.
Yeah, in that last slide you mentioned about the tolerant quantum device.
Yes.
So his question is actually the tolerant is related to what?
Related to what?
Yeah.
Okay. Good question. So as I mentioned, lambda levels, for example, charge powders, when we make some quantum transport, we need a very low temperature, very high magnetic field. We have some level broadening and we have to separate the level in some enough quantity. But if we use, for example, very local single defect with a certain series period or something, one example is this single defect resonant transistor. So in this case, we can probe only certain area of the graphene. So thanks to this local single defect state in the HBN, we can make more tolerant quantum devices. Tolerant means we can avoid the charge powder effect. So we can avoid some level broadening effect and we can measure it at room temperature, hopefully. So this is one example. Your question is great because overall, this is one example. So observing lambda levels at room temperature thanks to this small localized defect state, this is one example of tolerant device. But actually, except this one, actually with the Juhi Pandy as well, we are studying ferroelectric and ferromagnetic and many phase transition based devices. So in 2D materials, we have quite different ordering of electric dipoles, ordering of magnetic dipoles, or order some phase transition nature. So I'm looking for some high Curie temperature or some other high coercive field ferroelectric devices or some gate-driven phase transition devices. Normally, I call them tolerant devices in my 2D materials. Okay. So, but they are different topics.
Okay, thank you.
Thank you.
We have a question from online participant. Dr. Shrimanta Mitra is asking, in the RTT, you use tear and stacked MOS2 at 0 degree. How about rotated MOS2 layers? Will it have any effect on the tunneling current magnitude?
Okay, thank you for the question. So I'm going back to the MOS2. So here, I mentioned the unique thing is we made this lattice matching between two MOS2 layers. We used the tear and stacking method. And if you look at the band diagram like this, here we have current increase as we increase the voltage. This is normal because we are increasing the current. And then here we have peak at this band matching. And then if we don't have this lattice orientation, we don't have this current decrease because here we have empty state. So in the tunneling device, if we increase the voltage, we have larger, higher current. So to make this current decrease, we need a sort of a band gap feature or something, but here we use the same material. So the question is, what happens if we don't align the two atomic layers? the answer is we don't have current decrease. This is a resonant behavior purely based on the momentum. Because we know there are some empty state, we need momentum concept to explain this room temperature, robust and tolerant quantum devices in my terminology. Okay, thank you for your question.
I hope, Shrimanta, the question is answered. Yeah, Shrimanta, thanks for joining. Yeah. Any other question from the audience on conference room? Sure.
Also, students and other members.
Anybody from online?
I have a question.
Yeah.
So, Professor, it's a bit not clear to me that if you are using a MOS2 and then tearing it up and then stacking it, then why is your momentum changing? Is it because of some stacking fault or some?
Okay, Jui's question is, how do we change the momentum here? So, okay, the thing is here, if we increase the source drain bias, so we are making the two Fermi levels further apart, okay? And then electrons should enter initially, and quantum mechanically, we assume they enter the same energy level. So actually, we are not modifying the momentum of the electrons, just we are making this band structure more, so we have this band structure alignment change. And then if they keep the same energy, they should experience a different momentum state. So we have certain momentum and energy of the electrons, and then just we are changing the band gap, band diagram, and then we make this effect. Okay.
Yeah.
Hope this helps.
Thank you. Yeah, thank you.
Hello, is the question answered? I mean, like.
Yeah.
Okay. So I think Shrimanta is extending his question that he's still wondering about the Moire structures for the MS2 layer. Yeah.
Yeah, so I opened the chatting room, and then thank you for your great insightful question. My initial idea was to see some Moire effect, but it was not that clear. Maybe the Moire feature is reflected also in our device result. But if we have Moire, for example, for your information, here we have HBN MOS2, HBN MOS2. So we have some Moire band here. So somehow this transport IV, so this is a very simplified only conduction balance band model of the MOS2, but we should draw some additional band from the Moire pattern. But for now, we have only two clear features. This is shoulder and something. So it was enough to consider this band. But I want to see some Moire feature. For example, another example is this one, graphene HBN. If we have graphene HBN junction, if we do more gate sweep, for example, 10 volt here, -10, +10, or some larger voltage bias range, we may see the Moire band. Moire band is located somehow, it depends on the period of the Moire pattern, but in our case, it's located here or here. But in this case, we were so careful not to break the dielectric breakdown. So here, it was also enough. You see the simulation, we didn't involve any Moire effect here. But Moire effect should be there. Actually, and Juhi knows well, but we are studying this Moire pattern effect for ferroelectricity. So we observed some ferroelectricity originating from Moire pattern between MOS2 HBN and graphene HBN these days. But they are Moire pattern driven ferroelectric. Ferroelectric means we have some sort of first order phase transition. So we have hysteresis. So we are measuring something about Moire. Thank you.
Thank you, Professor Yang. So I have a question on slide number 25, where you mentioned about the graphene with 21-degree rotation.
Maybe this one. This one.
Yeah, next slide. Yeah, next slide. Okay, yeah. So here actually the bend structure is entirely different because you rotated it. And I'm just wondering because you know that right now a lot of research is going on the bilayer graphene with almost like 1 degree of the angle of rotation between the monolayer and the bilayer. So here you mentioned about the tunneling between the two graphene layer via HBN. And I guess the HBN are the 4 layers, correct? If I'm not wrong.
Yeah, 4 layers, about 4 layers. Yeah.
For the 1 degree rotation of the bilayer graphene, if you put the HBN in between, the correlation what people have been talking about the 1 degree rotation, is that exists even if you put the HBN as well, or it will be a little different?
Okay, very good question. If we make even magic angle graphene, but if we have HBN in the middle, the correlation would be very, very weak. So 2 different things. Here we have to consider moire between HBN and graphene. But in your saying, bilayer means moire between 2 graphene layers. So if you have in the middle HBN layer, we will see some moire effect between HBN and graphene, not the magic angle things. But of course, it depends on HBN. If we have monolayer, do we have some correlation and the strongly correlated features or not? I don't know. There might be some interaction, but mostly this moire between HBN and graphene would be concerned.
Okay. Thank you very much, Professor Yang. Any other question? Yeah.
So how difficult was this to how sustainable and difficult is to make those graphene?
So one of the PhD scholar is asking the question on the making of the heterostructures. How difficult it is to make these heterostructures?
Yeah, making heterostructure. So
Yep.
here I showed you the angle controlled heterostructure. Of course, GUI can do it well. So we have a special transfer machine. So we have some polymer and some general process. Somehow we have to make this rotation, relative notation. But you have to know that even though we set 1 degree between 2 layers and then stack them, it's not homogeneous 1 degree. We have strain and many things happens, and then we have some local 2 degree, 0 degree, 1 degree, and it's inhomogeneous. That's why we have some difficulties in reproducing the data, but now we also understand. So how difficult it is, it depends on how large uniform area do you want with a certain angle. Or if you don't care about the angle, just the heterostructure between metal semiconductor insulator junctions, it's relatively easy. In that case, the number of layers, mono, bi, we have different band and different direct, indirect band. So, or moire pattern, here we have to control the angle. So it depends on your purpose. The difficulty depends a lot. So for simple tunneling, we are using also simple tunneling for synaptic devices, things like that. It's very easy, but moire or some angles and uniform area, they are difficult, I would say.
Yeah, it is really difficult to make the heterostructures because you know that number one, you can't see through the eyes, so everything is under the microscope, and then controlling the angle is because, as the Professor Yang mentioned, it's relative change rotation of with the monolayer, like first layer to the second. Hardly, it's very difficult.
Our eyes become very tired. I don't like it.
Yeah. So yeah, with that actually, I think we can close the session for the question answer, and let us thank the Professor Yang for the excellent wonderful talk.
Yeah, thank you, audience.
Thank you very much, Professor Yang.